can hear me, right? Okay. Hi. Hi, my name is Yunjeong. Sorry, I'm hearing myself. There is an echo. Yeah, I will just start in the interest of time. I'll be presenting to you today my recent work on DSLs in Racket. Specifically, I will talk about language design objectives called design intents that language designers have, as well as how you can achieve these intents within the Racket ecosystem. And I will talk about how DSL authors exercise these intents and mechanisms for popular Racket-embedded DSLs. Before I get to these points, let me first illustrate what you can achieve with the DSL in Racket with the simple game engine language. Let's suppose that you want to develop a language for creating a Clickomania game. A Clickomania is a one-player logical game where it's initially populated with blocks of different images or colors, and upon each mouse click, all the adjacent blocks of the same image get removed. To implement this game, you need to write code for various logical and graphical aspects. Logical aspects such as choosing random images, removing blocks if they're adjacent and are of the same image, and populating new images in the empty blocks, and so on. Graphical aspects such as resizing images with respect to frame size or block size, and setting the background image as well as block images, and so on. Which means that if you were to write this in vanilla Racket, you would want to implement a data structure to represent a game state and a global variable in the form of mutable matrices to keep track of states of blocks, a function that eliminates all the adjacent blocks of the same image or color, a function for adjusting the size of an image based on a specified target size, and many more. But all of these code repeat in any Clickomania game, which means that they can be abstracted away in a DSL with a few lines of code. Okay, this aspect of abstraction is quite well known about a DSL. What else can we do with DSLs in Racket? Aside from specifying domain-specific functions, say if you, a language designer, want to use curly braces for a grouping of statements, as in C or Java, you can add this new syntax to your language. Or you can require all the DSL users to specify certain bindings in any program written in the DSL, and make the program crash if they fail to do so. Or you can ensure that your DSL programs can work with the host language programs through imports and exports. Also, you can allow the user of your language to write macros to extend the language itself. All of these are possible within the Racket framework. So now that we have briefly seen what it's like to use a DSL embedded in Racket, let's move on to the first contribution of our paper, a taxonomy of so-called language design intents. Language design intents refer to implicit objectives or goals that a language designer has in mind with respect to how their language look and feel or behave. I will describe each of the intents with the following 3 DSLs. A configuration language called frog-config, a type language called type Racket, and a shell-like language meant to work with this host language Racket called Rash. So first, custom syntax. While it is true that you can keep the host language syntax as in the frog config DSL. You can also add a new syntax for representing different information, such as type information for type racket. Even more, you can have a whole new syntax, as in the shell language part of Rash, or a combination of shell syntax and racket syntax. Moving on, the second intent is called custom semantics. This refers to DSL-specific meanings assigned to language constructs. Let's take a look at frog config DSL. This DSL provides bindings that are used for generating a configuration file. And likewise, Rash provides shell-like bindings as it tries to replicate behaviors of a shell language. Although we expect each DSL to have domain-specific bindings, as the name suggests, there are some nuances to be found here. For example, in type racket, while it has type racket-specific bindings, such as define type or other bindings here that are used for specifying types, it may override host language bindings, such as define here, to provide new semantics to the existing bindings of the host language. Now, shifting away from syntax and semantics, an interesting intent you can achieve is to control import and export related behaviors. An interesting DSL example to look at is frog config. This DSL requires all the program written in frog config DSL to export these three bindings: init, enhance body, and clean. Omitting any of these bindings will cause the program to crash. And in type racket, while it looks like type racket code is importing other type racket code, as in the racket code importing other racket code, the underlying behavior of import and export differs as it incorporates all the type information. However, Rash is an example of language without import and export control, as it is designed to allow its users to import or export other Rash code without constraints or additional information. Next intent is called macro support. That is, supporting the users to write and work with macros. As for Rash, because Rash is meant to be a shell language where the users can write normal Racket code, it intends its users to be able to enjoy Racket's macro system. Type Racket also allows its users to write Racket-like macros. Frog config, on the other hand, is intended for writing configuration files, so it is not meant to provide macro support. Moreover, a DSL can be designed to let its users read and write host language code as in the host language, and we call this intent syntactic embeddability. In frog config, Racket code can be read or written as in Racket and successfully compiles most of the time, meaning Racket code that exists in the frog config program is effectively embedded. Another language with this intent is Rash, as the language allows its users to switch between Racket and Bash language. On the other hand, when you look at type Racket code, you cannot read Racket code as if it's in Racket. Instead, it requires users to annotate type information. Hence, this is an example of DSLs syntactically embeddable under certain constraints. Next, DSL authors can develop a DSL to make it work with the host language, which is called interoperability. In other words, if running the DSL code results in values that can work with Racket code, then we call that the DSL is interoperable with Racket. Interoperability is almost always a feature and a goal in Racket-embedded DSLs, as in the case of these three languages. And lastly, Another useful design intent is to equip a language with an ability to statically check certain properties, hence called static checking. For example, a type racket is an example with this intent, as a common form of static checking is a type system, and this is a language where a type system is added to the language. On the other hand, both Rash and frogconfig are DSLs that do not statically type check or perform other static checking. Now that we have seen all the 7 design intents, let's look at the mechanisms that enable them in Racket. The enabling mechanisms can be categorized into reader customization and expander customization. The first category refers to customizing a reader. A reader is a Racket-specific parser that converts the source code into the Racket notation based on S expressions. In Racket, you can access and rewrite the reader of your language and do several things. You can reuse a parsing function called resyntax from the Racket itself, or you can add a new way to parse to handle parsing by adding this information to a parameter of the function called readTable, and use this as a new way to parse your DSL code. So once this is put together as a customized reader, now it can handle new syntax added to your DSL, such as curly braces or a block of statements, as we've seen earlier. Further, you can redefine a custom parsing function and provide it through the reader, and this will enable a custom syntax such as non-S expression syntax that looks more like a Python code here. Additionally, you can implement a reader that enables multiple syntaxes, such as my hybrid resyntax here, which allows both S expression-based syntax and non-S expression-based syntax. So, based on the extent to which this parsing function as well as its parameter are adjusted, we came up with a classification of reader: default, extended, custom, and hybrid. And when put together and linked back to the language design intents, this is what enables custom syntax of a DSL. Another set of enabling mechanisms has to do with expander customization. And for this, we have come up with 5 major ways to customize the expander environment: default bindings, custom bindings, default bindings at phase 1, custom module begin, and other custom implicit forms. I'll briefly describe them with examples. DSL semantics are refined through bindings provided in the expander environment. An expander environment consists of initial set of bindings which the Racket expander uses to recursively expand to a fully expanded program which can be understood by the compiler. As briefly listed earlier, you can choose to provide all the default bindings from Racket. You can provide DSL-specific custom bindings through this environment. You can provide Racket's default bindings at phase 1, where phase system is used to separate runtime bindings from the compile time bindings, but with more fine-grained details. Or you can provide redefined special bindings known as implicit forms, used to facilitate subtle customization of semantics, including the ones such as module begin for declaration of module here, or other forms used for function application, and several more. So when all the customization options are put together and linked to the language design intents, what we have found is that custom bindings and customizing other implicit forms enable custom semantics. Customization of import and export related bindings or customization of implicit form used for module declaration enable import and export control. Default bindings provided at upper phase 1, enable macro support. A combination of default reader and default bindings enable syntactic embeddability. And a combination of default bindings, custom module begin, and other custom implicit forms enable interoperability. And lastly, custom bindings and customization of implicit forms are the mechanisms that enable static checking. Further, we analyzed how popular Racket-embedded DSLs achieve these intents by customizing their readers and expander environment. We chose the 30 existing DSLs based on their popularity measured by their GitHub stars. So in the interest of time, let me focus on a few things that stood out. First, before this study, it was commonly believed that language designers are more likely to extend the Racket syntax rather than having its own custom syntax. This turns out to be true, but the difference was surprisingly not so large. Besides, a majority of the DSLs were using the default Racket syntax. Second, we hypothesized that changing these special bindings, known as implicit forms, would be uncommon due to complexity involved. However, when we looked at it, around 40%, 36.7% for custom module begin, and 43% for other custom implicit forms. So around 40% of the DSLs studied reinterpreted the implicit forms, changing some default behavior of the respective language. And lastly, as the DSL authors are likely to have written macros when designing their languages, we assumed that they would appreciate the extensibility of Racket. Hence, we expected a majority of DSLs are likely to support its users to write macros. It turns out that 2/3 of the DSLs studied provide macro support, confirming this hypothesis. However, 1/3 does not, suggesting that DSLs may intend to prevent its users from extending the language. So for more on the findings, please check out our paper. To conclude, in this work, we have proposed a taxonomy of language design intents, as well as their enabling mechanisms in Racket's ecosystem. And in particular, we analyzed existing Racket-embedded DSLs to make observations about how Racket's metaprogramming facilities are used to achieve the design intents. That's the end of my talk, and thank you for listening.
Am I on? All right. Any questions?
Hello?
Can you hear me?
Yeah, I can hear you now.
All right, thank you. Okay. So I guess one question I had was, what sort of hypotheses, were there any additional hypotheses that you didn't get a chance to present here, especially ones that maybe the results were different than what you expected?
So yeah, these were the three main, so we made 3 different hypotheses per, in our work, we presented 3 different hypotheses per reader customization, expander customization, and the design intents. And these are the ones that we found more interesting than the other ones. So I think the other ones that they were, so we got them from the Racket guide and the beautiful Racket book, the assumptions about the way people design languages, and they were mostly sort of confirming our hypothesis, but the ones that I presented here were the ones that I thought was interesting to discuss.
All right, thank you. Any other questions from the audience? All right.
I wonder whether you have perhaps used other sources than the source code of the DSL implementations to substantiate the observations that you have. Like in particular, did you encounter any discussions on the design decisions that you've learned something from?
Right. So we have looked at the source code, and we have also looked at the documentation and the description of the language. Some of the source code comes with some, some README documents or other additional documents that describe what they intend their language to be used as. So we were using them as the sources in addition to the implementation code itself.
Were there perhaps cases where if the language implementers had more knowledge about how to use macros, for example, or how to customize their syntax, perhaps they would have used other facilities of Racket?
You mean that they could have done things better or differently, but they were not doing that? In that kind of...
Yes, exactly. Perhaps because there was a knowledge gap on the facilities that Racket provides.
Yeah. So I suspect part of the reason why we see a majority of the languages use the default syntax as is perhaps has to do with the lack of awareness among the DSL authors about how they can customize their syntax. So I think, but that is just the assumption, and we didn't get to really talk to all the DSL authors. So yeah, and everyone's skill sets differs, so it's difficult to tell whether they were doing it because they were not aware of some of the meta programming facilities. Yeah.
Thank you very much for your talk. I think in the interest of time, we'll move on to